Okay, so what we're going to do, we're going to talk first about composting and about the composting process, how to have an efficient process, and specifically how it affects pathogens and the regulations associated. Then we're going to go, again, I already had a whole hour on anaerobic digestion, so we're not going to go over all of it. We're just mainly going to talk about the back end of it, the biosolids, and again, Class A biosolids, Class B biosolids, and the regulations on that. And then we're going to go into a little bit of antibiotic resistance and kind of what we know at this point and what we're trying to do to kind of unmuddy the waters there. So when we talk about composting, what we're talking about, again, is water, oxygen, microorganisms, feedstock. So let me take a step back, actually. So what we're talking about is manure treatment technology. So again, if you're a dairy farmer or a poultry farmer, you're just putting the manure on the fields. That's one option. The other option is to actually have a composting or anaerobic digestion process first and then put it on the fields, right? And there can be other feedstocks that are brought in with the manure. So this compost process can be different types of feedstock. So this is a process that can be just manure. It can be manure plus food waste. It can be manure plus yard waste and food waste. It can be a variety of grass clippings. It can be a variety of things here. But basically, it's just a feedstock. And in this feedstock, you have microorganisms, you have oxygen, and you have water. And during the process of composting, you get evaporation. You have water come out. You have CO2 from the respiration of the microbes during the process of composting. You have heat that's produced. So this is an aerobic process. So we talked about anaerobic digestion earlier and about how we actually have to add heat. We take heat from the generator and we actually put it into the digester to increase the temperature because that's an anaerobic process. It's not as thermodynamically favorable as composting, which is an aerobic process. So during this process, the microorganisms, as they're eating up this feedstock, they're generating heat, and that pile's going to get hotter and hotter and hotter. And that's a good thing because what that does is it accelerates the process and it actually destroys the pathogens, okay? So in aerobic composting, we actually don't want odors, okay? Because if you were in the anaerobic digestion, we talked about methane production and being an anaerobic process, and methane comes, and the other thing that comes is hydrogen sulfide, also an anaerobic. So if I go to if I step into a wetland and I step down in the wetland and I have this big gas bubble, okay, it's anaerobic. That gas bubble that I'm smelling, it's some methane, but I'm not smelling the methane, I'm smelling the hydrogen sulfides. It smells like rotten eggs. So if I'm going to a compost pile and I kind of, move the compost pile and I smell rotten eggs, that means that I have murky anaerobic soil, like compost pile, right? I shouldn't smell anything because if it's an aerobic process, hydrogen sulfide shouldn't be produced and it shouldn't have any odor, okay? So if you go to a compost pile that smells, that means most likely it has gone anaerobic, and so it's no longer an aerobic process and you're getting those hydrogen sulfide smell. So hopefully we're not getting odors. So again, the needs of the compost, it's a microbial process, and so it's the needs of any living thing. It needs food, which is the energy, the substrate. It needs oxygen, nutrients, water, and it needs a hospitable environment. And that means it needs a temperature that it can that's reasonable. But again, you can have compost in a cold climate because it generates its own heat. And you need neutral pH conditions so the microorganisms can live. So what the microorganisms do is they basically secrete enzymes, and that dissolves these organic materials. And we talk about the organic materials in a minute. And so they break these bonds, and then they can utilize these small organic compounds. And again, in this composting process, it's not just bacteria. We also have other organisms that are involved in the breakdown of the organic material. So what is organic material? I keep saying this. So it's basically anything derived from living organisms. So it is leaves, it is tree roots, it is food waste, it is manure, it is animals can be organic waste, right? So it's organic matter is anything derived from living organisms. It contains carbon. It's a source for decomposers, which is what composters are. They're decomposing this organic material, and it contains other stuff, nitrogen, phosphorus, other things in there as well, in varying ratios. So when we look at organic matter, there's varying types. So we have some organic matter that are sugars and starches, and those are going to be the ones that will break down first, and that are easy to degrade. And then we have the proteins and fats, then the cellulose and hemicellulose, and finally the lignin and lignocellulose just takes longer to degrade. So it's going to be the one that's most resistant to this decay. So that's going to be more like your tree barks and the stuff that has a high lignin content. So again, if we look at a pile of compost, there is a lot of microorganisms. We don't even know most of the microorganisms that are in that compost. So when we look at compost or we look at even soil, the idea is that this is full of microorganisms that are doing this process, and hopefully the compost is nice and aerobic, so all the organisms in there are aerobic organisms. So there's 3 main stages. So we talked about in digestion about mainly being in this mesophilic stage. That's only the first stage for composting, okay? So you first have this mesophilic stage. That's going to be your 68 to 100 degrees Fahrenheit. And so that's going to be just starting the compost pile. It's going to be mesophilic. But then what it's going to do is it's going to quickly rise to this thermophilic stage. And this thermophilic stage is 105 to 150. And then it's going to start to go down to this curing and maturing part where it goes back down to the mesophilic phase. So why is this so important? It's important because we need, this is your average ambient temperature, and we need it to actually go up to 140, a little less than 140, 131 really, to get most of our pathogens killed. We need to get the pathogens killed. Then if we need, we can also get the weed seeds killed if we go a little bit above 140. But the problem is we don't want it to go up to 170. If we go up to 170, we're going to kill off everybody, right? So we want to stay in that nice range of like 130 to 150, where we're going to get our pathogens killed off, but we're not going to kill off all the rest of the bugs. So when we talk about turning is really important in composting. We do have often the turning, and we'll talk about this, but a lot of it has to do with we want to keep it aerated, right? We want to keep it nice and aerobic. And so what happens when we turn, you know, people are concerned about turning because you have the temperature going up and then you turn it and it does go down. But what happens then after it turns, it goes back up higher. And then it gets turned again, it goes back up again. Because the idea is what we're doing in turning, it's about contact time. We're taking those microbes that may not be in contact with the food, the organic matter, and we're kind of redistribute them. So then it's actually, they're going to have new material, there's some sugars and starches and other things that they haven't broke down yet, that they're now in contact with that they weren't before. And then it's going to increase their metabolic activity, which increases the heat produced, which increases the temperature of the pile. And then we're going to turn it again because then it starts, they've kind of used everything in that little area. And then we're going to turn it again and redistribute, and then we're going to see it go back up again. So turning is actually important in increasing the activity and increasing the contact between the microorganisms and the organic matter. Yeah, so
compost, which I've been composting for 5 years, and it's the best. There's never been any chemicals involved.
How often do you turn it?
Off and on, frequently, and then for a while, then I stop.
Yeah.
It varies, and I'm amazed with it. It's just like beach sand. It goes through your hand just in.
Yeah. Well, that's exactly what you're supposed to do. You turn it.
There's no smell. There's virtually no.
Yeah. So we've had farmers who actually, there is kind of a sweet spot in that you don't want to turn it too much. We've had farmers that have turned like every other day, and what we found is they didn't get that high rise in temperature. It was too much turning. So we do want to leave some more time. So here in this example, for example, you saw that they're turning again about every 10 days. You see 5, some will push it 5, 6 days, but it really depends on the process and how easy it is to degrade the substrates that you're putting in there. And so, and it also depends again on your porosity and how aerobic it is. So we'll go through some of those things. So there isn't like a set date, like you turn it every this many days. And you're actually going to lengthen the amount of turning as it goes through this process. And then at the current curing stage, as you said, you're going to kind of stop doing it. And so that's exactly what you're supposed to do.
I have brought it back. I'm like, I will turn it off and on for a period of time, and then I just stop.
Yeah.
I might stop for maybe a couple months or so.
Yeah,
and then
that's
I
right.
go back and then I regenerate the heat right back again, and it goes up between 130 and 150 degrees.
Yeah.
Rarely brought it up over that.
Yeah, that's where exactly you want to be. That's perfect.
I fucked up on that. I don't know how.
No, that's perfect. So again, these different phases. So again, we talked about that first phase being that mesophilic stage. So that's where they're going to break down that really easy stuff, the starches and the sugars, and that's going to make the pile rise. During the end of this phase, we actually have some bacteria that are going to develop endospores, and those endospores are going to protect those bacteria that aren't heat tolerant, okay? And so what's going to happen is then the next phase is where the temperature really goes up. So then you have the thermophilic bacteria and the fungi. They're going to take over, and they're going to actually do a lot more of that degrading at these really high temperatures. And these heat-tolerant microbes go dormant, and this is where the pathogens get destroyed. This is where the more complex material starts to degrade, and the proteins and the hemicellulose, and again, the temperature starts to rise. Then the last phase is what you were talking about. It kind of returns back to another state, and this is where again, we're getting rid of the rest of the proteins and the carbons, and the temperature starts to drop, the lignin is going to start to decay, and this is the area we're actually going to see the earthworms come in, and the arthropods, and some other things. This is that final kind of curing stage, and so we're going to see every other things come in, and there's still a lot of material to eat and make it nice and fluffy. So if we look at this, we have the bacteria coming in, and this is going to be, again, mirrored by the temperature. And we're also going to have our other organisms come in here during this time and help with the process. So it's all of these organisms together. So the key processes, the first thing is looking at the feedstock. So when we look at your raw materials, you're looking at what's the organic matter, what's the nutrients, what's the degradability. Again, are you using a lot of like branches and things that are hard to degrade, or is it food waste, which is going to degrade fairly quickly? What is in there? Manure. What is the moisture, the bulk density, and how heterogeneous is it? And again, do you have any contaminants? What's the costs and regulations associated with your compost? So if I'm a dairy farmer, I can compost my own manure on site, under roof, without roof, however I want to do it, and I can lay it on my fields. That's fine. Okay? If I'm going to bring in food waste from off-site, I can still do that, and I can compost it with my manure. The difference is I have to build a concrete pad in order to, that's the regulation for Maryland. Now it's different for Pennsylvania. But in Maryland, they say, okay, if you're going to bring off-site organics onto your farm, then you need to have a concrete pad, and then you can compost, and then you can, sell it, use it on your own land, whatever you're going to do. So there's various regulations based on where you're located in terms of how it's managed. So again, the first thing that we're going to talk about is basically the nitrogen, because again, we have the carbon, which is the organic matter, but then we also have the nitrogen. The nitrogen is very important because that's a nutrient source that's needed by the microbes. And so we might find that in the grass clippings, in the manure, and the food waste. And the carbon-nitrogen ratio is very important. So the idea is there's so much carbon, so much nitrogen, and actually phosphorus too, that organisms just need. We need a lot more carbon, and then nitrogen, and then phosphorus to for our metabolism, and microorganism metabolism as well. And so the CN is how much more carbon to nitrogen. So what is the carbon to nitrogen ratio? But it doesn't tell you anything about how easy it is to degrade those carbon. It doesn't say if it's tree branch carbon or food waste carbon. It just says it's just the carbon to nitrogen ratio. And so what ends up happening is we have an ideal ratio, which is the same for digestion as it is for composting, about 25 to 1. That's how much carbon we need to nitrogen. What happens is if you have too much carbon, if it's 40 to 1, then what's going to happen is your microorganisms are starting to be limited, just like with crop growth. We're going to be limited by our nitrogen. And so we're not going to get as much activity because we're nitrogen limited. If we're the other way and our CN ratio is low, so we're like 10 to 1, then what that means is we have so much nitrogen that it's more than the microbes can use. And so they're going to be carbon limited, so we're going to have less activity, and that nitrogen is going to start to volatilize as ammonia. Okay? So one of the things that we're going to think about too is particle size. Okay? So we talked about in digestion, we want to break up that particle size so that we can increase that hydrolysis step to make the process happen faster. In composting, it's not that simple. Yeah, we want to break it up a little bit, but we don't want to break it up too much. Okay? Because what happens is we still need it to be nice and fluffy and porous, and we need the air to come in there. So if we break it up too much, then we're going to decrease that pore spaces. But we do want to break it up some so that they can get at it. So if you think about, we're talking about here's the surface area that we have, if we break it up but still have some material, then it can get around that surface area without reducing too much of, we still need rigid particles to help provide that structure and aerate. So again, porosity is very important. Free airspace, FAS, you'll see this on a couple slides. And what that is it's the amount of pore space that's not occupied by liquid. So porosity is just what's not solid, okay? And then we have the free airspace, which is not occupied by liquid. And it's going to vary from pile to pile, but we want to start with more than 50% porosity. So we want this to be nice and fluffy when we start because we don't want it to go anaerobic, because if it goes anaerobic, it's going to smell. So here's our compost particles. Here's our pore space, okay? But we do have liquid film around our pore space, and that's our free airspace, okay? And we want to make sure that we have enough of that free airspace, again, about 50% when we start our pile, so that the airflow can get around the particles. So this is also related to the bulk density. So the idea of bulk density is how much does a certain volume weigh? What's your volume to weight, okay? So with our bulk density, it's the mass per unit volume. For compost, we actually want it to be, again, we can think of water, we can think of topsoil, but we want our compost, we don't want it to weigh a lot per cubic foot. We want it to be nice and fluffy, okay? So that's something to think about. The lower bulk density means that it's going to have greater porosity and free airspace. So you don't want it to be real thick. You want it to look like this and not be stomped down because we've reduced our free airspace. Okay. So again, our initial dosicity, again, we want it above 50%. And again, these are some bulk density things you can go back and look at in terms of the actual values. So the next is pile moisture. So again, optimal is about 50% moisture. So that means that if we have more than 65% moisture, that means that it's kind of wet. And what happens when it goes wet? It goes anaerobic, right? And that's where we're going to start getting the smells. The problem is if it's too dry and it's less than 35% moisture, then we're going to start getting dust, okay? So we really want to, that's when we're going to start, we need to wet our piles and to keep the dust down, okay? So where we want to be is at 45 to 50% moisture, okay? In terms of aeration, again, these microbes need air. It's an aerobic process, okay? So we need to provide them with oxygen. That's actually what they need in the air. Again, if it's below 10% oxygen in the pile, they might start switching to anaerobic respiration, which means we're going to get hydrogen sulfide productions, which means we're going to get odors. So again, if we maintain that adequate oxygen, we're going to reduce our odor complaints. So again, we might be forced air. We might actually not even have blowers, but we may actually just through convection rely on diffusion and convection to get that. But again, it's going to be controlled by the compaction, the particle space, and the moisture. And so when we look at the pile shape, larger piles tend to get hotter. So that's good because that kills our pathogens, right? But if they're too big, we need to be careful that they're not too bulky on the bottom. We get compaction on the bottom, right? So we don't want them to do too heavy or they compact. But we want them to, the small piles, again, if it's too small, then we'll have better airflow. But again, we may not get the heat that we want. So it's kind of this pile management. But it's going to probably match our equipment size. So our pile's probably going to be dictated by what we're using to turn the pile. Yeah.
I found online, I don't know what anybody else is doing, but about 100-ton piles seems to work for me really good. That's up about 4 feet, 4.5 feet high.
Mm-hmm. And how wide?
And wide digestion's probably about 8 feet, I
Mm-hmm.
think. And I haven't had the problems with anything like
Yeah.
you're saying can
Yeah.
occur. I've been really, I've just done it all by hit or miss over the last 18
Yeah.
years.
But I mean, when we go to compost piles, and honestly, it usually comes, I'm little, but it usually comes to about here on me, and that's usually a pretty good pile, and then I usually can't get my hands around it. So that's kind of a general rule of thumb in terms, but a lot of it has to do with the windrow equipment that they're using. So that's gonna dictate it a lot. So again, are we undercover or not? And if you're not undercover, then again, you can shape to capture water if you need more water, or you can actually shape to make the water drain out. It depends again where you are in your moisture content. In terms of temperature and retention time, again, the higher temperature, the faster it's going to go. But we don't want it to go too high, or we're actually going to lose some of our microbial diversity. Again, that 131 is kind of the key temperature that we use in US regulations is 131. Above 131, we've killed off our pathogens. That's what we use in our regulations. So there's this process to further reduce pathogens, PFRP. So again, it's the time and temperature requirement to ensure that we have pathogen reduction. So if I have an aerated, so I'm forcing air in, aerated pile or an in-vessel system, I need it to be 131 degrees Fahrenheit or higher for 3 straight days. Okay, that's what I need. If I have a turned windrow, so more of a windrow, and I'm turning the system, I need it to be 55 or higher for 15 days or more within my 5 turnings. Okay, that's my regulation. And that's, again, to reduce pathogens. That's why we have it there, because it's that 131 magic number. Again, this is it. That's why we do it. We want to make sure that we hit that thermophilic stage. So again, time. So first we're going to start in that mesophilic for a few days, up to 2 weeks. The thermophilic is going to be 3 weeks to several months. It depends on your material, the carbon-nitrogen ratio, how high your temperature is. It just depends on all that stuff we just talked about. And then your curing can be 1 to several months. You can cure it for 1 month. You can cure it. Your curing is basically done when it looks nice and fluffy and you can't tell the original material that's in there. So when is it done? The pile is less than 10 degrees warmer than the ambient, so it's basically not hot anymore. About a third of the original volume. You can't recognize, there's no broccoli pieces in there. You can't tell what else is, what you put in there. You can't recognize the material. It's dark. It smells earthy, not like rotten eggs. And it's, again, stability. And you can take it to the lab to actually look at your organic matter before and after and see where you are in terms of the degradation for outside lab testing as well. So again, I'm not going to go over all this, but you'll have this in your materials. But again, the preferred range of moisture, carbon, nitrogen, oxygen, temperature, particle size, and porosity, and what we need for a good compost. And again, we care about this because good compost means good pathogen kill. That's why we care.
So we have a manure lab, and they'll give us a CN ratio. They state that it's not an EPA method. So they determine those 2 elements, but
yeah. So what they're doing, so I don't know the specific one, but there's machines, they're called LECO machines, that actually does a CN ratio. So you actually have a little particle, you put it in a tin, put it into the instrument, and it basically combusts it, and it gives you a CN ratio. The other thing you can do is do volatile solids, which I talked about in the other presentation, which is basically your organic matter. It's basically you put it in a furnace, and it's what leaves you. So it's the difference in weight between you weighed it before the furnace and after, and that's your organic matter. And then you test the nitrogen, and then you call it a CN ratio. Okay? So they're probably doing that. They're testing the volatile solids and calling that C, which is approximate for C. And then they're testing the nitrogen, and they're giving you a CN ratio versus actually using a CN analyzer. So I'm assuming that's what's happening. It's pretty good, but they're saying it's not EPA because it may be, if you go to the EPA method, it may be slightly different. So, yeah.
still usable.
Yeah, it's fine. Yeah. It's approximate. It'll get pretty close. Okay, so again, there's a lot of different methods. We might have the window internals, we might have static piles and vessel systems. Again, there's a lot of different composting, vermicomposting, a lot of different things that we can do in terms of composting. And a lot of, again, these are all different types of in-vessel system. There's lots of manufacturers, different composts out there. And then you have screening afterwards. Again, screening isn't necessarily required, but it's, again, depending on what you have in there. So again, if we're taking especially a lot of food waste, we probably want to screen out some of those materials. On campus, for example, when we go to our compost facility, there's forks in there, and there's rubber bands, and there's plastic bags, and so we definitely have to screen. So screening isn't required, but it depends on how you're selling it and what you're taking in, and what screening processes you're going to use. Again, so when we look at what drives composting, Again, it's based on local jurisdictions. What I'm doing in one state is different than another state, and one county is different than another county. So the University of Maryland, for example, we used to send our food waste to Howard County years ago, and that food waste actually facility was closed down by the county officials because they were having concerns, not only odor complaints, but they were having a lot of like plastic bags blowing around. Like you literally go to the facility and it's like, it was just a mess because they weren't doing the source separation right. And that's really important. How are you managing as it comes on site? So then we sent it up to Delaware. Because again, we were trying to be sustainable with our food waste. Sent up to Delaware. We sent it there for a while, and then they started to get some odor complaints, and so they went on their own and said, we don't want to take your food waste. We think it's too wet, and we think it's turning it anaerobic, and we don't have enough like other material to compensate, so we don't want your food waste anymore. So now we're finally, we got PG County to build a huge new food composting facility. They just built it. And so now they're taking food waste from the university plus all the garden waste and grass clippings and things from around the county so that they have a nice ratio in terms of keeping that carbon and nitrogen right and the moisture content. So that's where we go now, finally, after a lot of sites. But a lot of this has to go with the regulating authorities and where we are, okay? Again, it's going to be the economics, the production, where are you selling this? What is the bottom line in terms of the economics? Are you using it for your own, or do you want to go to the bagging and production phase because you want to sell it off farm? And then the food safety requirements, which we'll go through right now. So again, there are some outbreaks that have been gone back to the use of compost. Again, the idea was that that if there's a lack of kill step in the processing or which we'll talk about. And again, the idea is this is a liability concern. And so right now there are retailers who are requiring third-party audits of the compost that you're delivering. So they will require you to actually have a lab that tests it for you. And again, this is a lot for leafy green tomatoes, melons, things that in the past have had outbreaks of things and things that often aren't cooked. And so they want to make sure that, that they're not going to get sued. And so again, they'll documentation of the soil amendments used in the field, because the thing is for compost, you can document, there can be a lot of documentation involved because compost is both a product and an input. So it's everything that went into the compost pile, right? But then that is an input for somebody else's crop. And so then they have to document everything that they did for that crop that they're using it for. So with compost, there can be a lot of regulations involved because, again, you have all of the documentation to create the compost and then all the documentation of using the compost for creating the produce that is going to market. So there is this whole hazard analysis and critical points control, HACCP, okay? So when we look at composting, what you're going to look at is first you're going to be the generator, the source separation. Where are you getting your organics, your manure, whatever you're putting in, where are you getting it from? And a lot of that's going to have to do with the delivery and input. Are they using, what truck, are they putting a cow, like a dead cow, is that going in the truck, and then the next truck is getting the food waste, and the next truck is getting this? You know, what's going into that truck? What's the vector control for that truck? Is there any cross-contamination? Again, once it comes on your site and your farm, if you're composting on farm, where are the points that it comes in and comes out? Is there a clean area and a dirty area? Then we have this thermophilic disinfectant phase. So regardless of what happens here, we better have this disinfectant phase. And in that phase, are we doing the pathogen time and temp limits? Are we eliminating vectors attracting? Are we getting, when we're holding it, are we getting rats in our holding area, right? Or during the compost, are you getting vermins and birds and things in that as well? So how are you controlling access? And then when we're curing it, again, this is where we're having nutrient stability. So we need to worry about cross-contamination because we've already done our thermophilic stage, right, at this point. So if we have a machine that's going to a pile that just started, and then we're using it for our last turnover here, when we already did our thermophilic stage, and that one hasn't had its thermophilic stage, we may be cross-contaminating with our equipment. Then we've got to look at, again, this drying and screaming. Again, what is the cross-contamination, personnel, and then we're looking at the product prepped, and again, we might be sampling. But this is, again, are you bringing your product in the same truck that you're taking it out in? You know, if so, you might be getting cross-contamination. So again, this is where we're looking in terms of these critical control points for pathogen reduction. So again, the who, what, and where of everything in terms of sampling, that's going to be your EPA 503 guideline for biosolids compost. The U.S. Council has all the information that you need in terms of testing and what you need to do. But again, a lot of it has to do with reducing cross-contamination from probes, tools, containers, shipping, and whatnot. So this is, again, just the microbial limits for compost used in EPA agriculture. Some is required for you to test, some of it is for you to test. In England, they specifically have, in the UK, they specifically have, again, for their minimum temperature, it's 60 degrees for composting for a closed reactor for 2 days. Biogas is 57 degrees for 5 hours, and then composting, again, is 50, 60. So again, that's a little bit different than what we have. What we have is, again, this 130 to 141 for 3 days in vessel, and then 130 to 170 for 15 days with 5 turnings. So again, they're a little bit different, but these are the requirements that we have. In terms of, this is the National Organics Program, raw manure. You cannot have raw manure put onto a field within 120 days of harvest. There's if it's carrots or something that touches the soil, okay? If it's like oranges, then we can't have it within 90 days, okay? In terms of produce, raw manure is not allowed within a year, okay? Compost has to follow this protocol, which we just went over, these things here. And testing isn't required, but the idea is that you use this process controls to reduce the pathogens. Again, these are the pathogens numbers that we have to keep under from that the prior table. So this is what we're trying to keep under in terms of these different Salmonella, E. coli, and whatnot. So again, the idea with this composting is that we're reducing, we're retaining nutrients, we're reducing NO2 generation, we're enhancing soil quality, bulk density, we're reducing soil erosion and improving the water holding capacity. By using this compost, we just need to make sure that it's safe. So again, it's process optimizations, your role, and again, looking at what the end use in mind and the compost value chain. So again, this is just the pathogen survival. We really want to think about the temperature, the moisture, and any competition and other things that we have here. Okay, so I already talked for an hour about anaerobic digestion last session, so I'm not going to do it again. But what we have in an anaerobic digester is we have, these organics can come into a digester instead of doing compost. It's an anaerobic process. You get actually energy out, which you don't in compost. You get it in the form of biogas. You can use that for electricity or renewable natural gas, okay? So this is the process we concentrated on in the last hour. Now we're going to talk about this process here, what comes out the back end, okay? So if you're on farm, really, you have the digester. You're going to manure storage and apply to the fields. You might solid separate and apply the solids and then the liquids. You might solid separate and use the bedding, but you're basically staying, this whole process is keeping on farm with your regular farm management equipment that you have. Through these different processes, we have the benefits. I'm not going to go into all these. It depends on what you're putting into the digester and the production that you have. Again, whether you get mesophilic or thermophilic. So, and these are the benefits of digestion, which we've already gone over. So the organic fertilizer is again, the idea that we produce this fertilizer that can go directly on the ground. It can be solid and liquid separated, or it can be the whole thing. And again, we've seen increased uptakes of nutrients after the digestion process. And again, but it has to fit into the nutrient management plan. Whether you have a digester or not, you have the biosolids from the digester, it fits into your nutrient management plan. So we don't have specific bacterial requirements for using this digestate. If it's before digestate or after digestate, it's just manure, right? If it's on farm. Where we have the requirements is when you go to a wastewater treatment plant, right? Okay, that's where we have the requirements in terms of biosolids class A, class B, okay? So again, the idea with the wastewater treatment plant is you have this consumption, you have urban nutrients go to a treatment facility, treats it, but then the solids, these biosolids, are then put on as crop fertilizer, and the idea is putting them back into agricultural fields. Okay, so what this process is, if I'm a wastewater treatment plant, I have this primary settling. This settling, primary settling goes to this digester, secondary settling goes to this digester, and then again, all of the after digestion, I do solid liquid separation. The solids go to the fields and the liquids go to the front of the wastewater treatment plant. If I don't have a digester, I'll show you that. It just basically, I just solid separate, the solids are lined, and then I put them as class biosolids onto the ag fields. So with the digester, we have, again, these solids come here. We have this digestion system. This is for DC water. They have a candy process that I'll talk about, and then they have class A biosolids. If there's any solids that skips the digester, then you're basically going to have to buy lime, and you need to lime it all, because that's going to kill the pathogens. Without digestion, you don't have a pathogen kill step. And so what they do is they lime it, so the pH goes up to like pH 11 or 12, so then the microbes can't live, and then you apply it to the field. It's a lower quality fertilizer because it's a high pH, and it's with the digestion process. Again, we talked about digestion. We're decreasing the amount of organics, but the nutrients are still there. So what that means is we have about half the amount of solids after digestion that we would before digestion, but it's like high quality. It's all the nitrogen, phosphorus, and less solids, okay? And that can be applied to the field. And they have this thermal hydrolysis process in DC water, so they're basically pressure cooking it and then putting it into these big digesters. You can actually see these going to 95 if you're going down north in Northern Virginia, the big digesters off the highway. So the thermal hydrolysis process, basically they're pressure cooking this thing. They're basically literally raising the temperature, raising the pressure, killing off anything. And then after that, they put it into the digester. So what that happens is they produce class A biosolids. So again, they're doing above and beyond what needs to happen because they're doing 160 degrees for 20 to 30 minutes. So it kills off everything. And those that don't go through this process, another waste plant would only have class B biosolids. And then they would have to add this line, which would be at a cost to them, and then test for the coliforms to make sure they're enough, which they don't they don't get any coliforms left with the bioprocess, with the biodigesters. So still, with this process, they still have to, as a wastewater treatment plant, control vector control. Even though it's Class A, they've got to make sure that they don't get rats and mice, and it's not sitting around, and they're not getting pathogens coming into the system. So they still have a vector attraction reduction that they have to meet and show that they are decreasing vectors and not introducing bacteria. Again, these digesters produce 8 megawatts of electricity. That's enough electricity for 8,000 homes. It runs the wastewater, it runs part of the electricity for the wastewater plant, which used to be the #1 user of electricity in the whole DC area. Now they're not. They used to be. And again, the big savings was actually $10 million in savings in trucking costs because they have half the material to truck out at a higher economic value than they did before. So we've some wastewater treatment plants return back to the field. In Germany and in Europe, some of them just incinerate. Even in the US, we have some incineration wastewater treatment plants. But in DC water, again, 99% of the nutrients and the biosolids are put back on the fields. Okay. And so here's the product that they have, which is the Bloom product that, again, is put onto the fields. And again, you not only have the Bloom product, this is actually Cowpots products. This is a digester that actually, after digestion, they separate the solids and they put these solids into these things called Cowpots. Pathogen-free, they have a lot of nitrogen and phosphorus, so they do a solid separation then a drying process, and you can buy them off Amazon, and they are from digested cow solids. So you can use it as that. Again, a lot of people just use the digested bedding, then they use the digested solids as bedding, but you can also sell them off farm and make fun products too. So this is the Bloom product from the DC water. They're trying to get it to sell in Home Depot. That's the goal, as an organic fertilizer. Okay, so the last 10 minutes I'm going to spend on antibiotics. So the idea is that we're doing all this manure treatment technology, and we're looking at, odor reductions, pathogen reductions, greenhouse gas reductions, and selling this on the market for anaerobic digesters. But what about these other things? So again, nutrients are transformed, but they're not really reduced by that much. We have to do something else to reduce nutrients. But what about antibiotics? What about caffeine, estrogens? What about wastewater treatment plants? They right now required to test for cathins and estrogens and antibiotics in a wastewater treatment plant because, to tell you the truth, it's really hard to do. We do it in our lab and it's not fun. And we get recovery rates sometimes at 20%. We spike it and we don't even get the recovery of what we spiked. It's really hard to do because if I was to spike in a sample from the river and spike it, I'll get 100% recovery. I spike in a manure matrix and I have to put it through my HPLC that has a tube about this small that has to be, so I have to do an extraction process and a digestion process and everything and then put it through. It's really hard to get recovery in manures. So again, they're not required to do it because it's not something that a wastewater treatment plant could really test for right now. But the idea is this is a concern? Why do we care about antibiotics and other types of these particles? Well, the idea is, again, in the U.S., we use a lot more antibiotics for animals than we do for humans. Where we are right now, we have a lot more animals than we do humans in the U.S. So that's understandable. But again, we have about 3/4 of our antibiotics is used in livestock, about 1/4 used in humans. So of these that are used in animal husbandry, the ones that are most used are tetracyclines, which are medically important, which means we use them in human use. Ionophores are not considered medically important, so we don't regulate those the same way we regulate medically important antibiotics. So why do we care? So we care because of this idea of antibiotic resistance. So antibiotic resistance is if I have a bacteria and I have an ear infection, my dog has an ear infection, my kid has an ear infection, I take antibiotics, right? And what happens is that antibiotics are going to kill off that bacteria that's causing this infection. Well, some of these bacteria can actually develop resistance to this antibiotic, especially if I keep treating it. But even if I don't, sometimes first time, they can develop resistance to this antibiotics. And so they have bacteria that survive that are resistant, or they develop the resistance. These bacteria that survive then can then go and through this process called horizontal gene transfer, they can actually take that resistant gene that they have and give it to another bacteria somewhere else in the environment. And that gene may have never been exposed to the tetracycline, right? So then that bacteria, I drink some water, I get that bacteria in me, and now I take tetracycline for the first time and it's already resistant even though it hasn't been exposed. Now that can happen in water, that can happen in soil, this horizontal drain in guts. So again, once this is acquired, then I get sick, I go to the hospital, and they try to give me different antibiotics. It's not working because the bacteria that proliferated in my body was resistant to that. They try a different one, and you know, we have these superbugs that are resistant to multiple strains of antibiotics. So that's why we care. So where do we have? We have antibiotics that are used by humans, we have antibiotics used by food-producing animals, and some used with crops. And so again, those antibiotics used by humans go to the wastewater treatment plant. The antibiotics used in livestock. Again, if I'm a dairy farmer and my farm and my cow is sick, I'm going to treat that cow. Like it's poultry litter. Maybe poultry farmers. Maybe the one chicken I can get rid of, but that cow I'm going to treat. And so I treat this cow. That milk is then not going to go into market. I have to keep the cow out of production for a certain amount of time after, depending on how long it was on antibiotics and what type of antibiotic it was on. That milk is I might actually put the milk to the calves, or I might just throw the milk, okay? But the manure is still going into the manure chain, right? And that milk is probably just being dumped. And so we're still worried about what we are going to do. So we're trying to stay ahead of the game. We don't have regulations for this in place right now in terms of the manure. What they do have regulations for is the Veterinary Food Directive. And the Veterinary Feed Directive basically says, this came into existence in January 2017. And it basically said, okay, in dairy farmers used to have you just bought the feed, and the feed had the antibiotic in it, and you could give it to all your cows. You can't do that anymore. What it is now is if my cow's sick, I have to get a veterinarian to write a prescription to treat that cow, okay? Then it might be an instance where like enough cows in the barn are sick, well maybe the veterinarian will say, okay, no, you need to treat the whole barn. But normally you would just treat the individual cow. You're not just having antibiotics in the feed that is being used by the cow. So that's the new directive. It's a federal law that started in January 2017. So, it only targets these medically important antibiotics, not the ionophores. And again, I must contain a prescription from a veterinarian. But states can have other regulations that follow this. That's just the federal law. Again, the ban, there was the idea when it first came in that it was going to really affect the industries, and the idea that it could decrease profits by up to $1,400, but we haven't seen that yet. And in terms of dairy producers, we actually saw that they said that it hasn't really decreased their again, it's only been in effect for 1.5 years at this point, but there was a study at Cornell, and they said that it hasn't actually decreased their bottom line, but what it has done is it's a little bit more paperwork, because they have to call the vet, and the vet has to come, they got to fill out paperwork and do all this stuff. And it's also, what they're doing is they're doing more capital investments to actually separate sick cows in a ways that they didn't do before, separate calves in a way they didn't do before. So it has increased their capital investment because now they can't treat the whole barn. States, Maryland and California, the only 2 states that have passed federal laws that are more restrictive than the veterinary feed directive, okay? And again, the key difference is California is a little bit more stringent, but what they've done is they've had extra laws that have to do with the preventive use of antibiotics, in addition to you can't use them to prevent diseases on other animals and things like that. We still can use them with a veterinarian feed directive, but what you can't do is it restricts how proactive you can be, okay? The poultry industry, i.e. Purdue, has gone antibiotic free, and it has nothing to do with industrial regulations, industry regulations. It has to do with marketing. Okay. So what we're looking at is the antibiotics in this manure, and seeing with manure treatment, how can we actually reduce antibiotic resistance in the manure stream? And what we found is, this is just looking at antibiotics coming in and out, and what we're finding is the antibiotics, we don't see antibiotics in a lot of our farms, nothing, and then we just see these spikes. And again, this is usually in February and March, when you get spikes in respiratory diseases and you get spikes in tetracycline. So it happens. And again, we looked at the genes, and what we found is we did, from what came into the digester, we definitely see a reduction in genes, especially tetracycline genes after digestion, but not by a lot. We're not seeing 100% reduction. And this is mesophilic digestion. And again, we looked at composting, and these were some static piles that weren't turned properly. And we said, does it affect? If we don't go to that thermophilic temperature and keep it at mesophilic, do we see reductions? Not really. Versus if we have the nice thermophilic, we're seeing reductions. And the same thing with the digestion. We're basically looking at, well, maybe we need to do these more high temperature processes. Maybe it doesn't need to be mesophilic. So what we're actually doing right now is we actually had, again, I talked about this in my last section, but what I didn't really point out is we had this whole section on antibiotic resistance. So there's about a dozen different fact sheets and different materials online. You can write this down, take a picture of it. The slides I think will be available. On antibiotic resistance and specifically with dairy manure and what dairy farmers can do. Trying to stay ahead. The issue is the science is murky. And so how do you prepare farmers for a regulation that might not happen or might happen with science that is not clear what we can do about it? And so we're looking at high temperature, and we're looking at a lot of extension efforts figuring out how can we help. I mean, dairy farmers have enough to deal with right now. So with milk prices being so low, so how can we help them in a sense of trying to stay a little bit ahead of the curve, okay? So the last thing is, if you're in my anaerobic digestion, you already got this pitch, but I'm gonna give it to you again, because I know we're all leaving at the end of the day, so buy the water container, as well as here, there's information on an anaerobic digestion survey. Anyone can take it. Based on who you are, it'll direct you to different types of questions, industry, extension agent, farmers, and you can even give this to other people. It's one of my graduate students is doing a survey for his project, and I'd really appreciate high participation. And with that, I'm done.
Question?
Yes?
So, did you do any herbicide bioassays on compost?
I don't, personally, but I'm sure there's people that do. Trish? Herbicide, the effects of herbicide on compost, the effects of herbicide in compost. Carryover herbicide in compost.
Yeah, talk to me afterwards. I talked about that in my talk.
Yeah, that's who I thought would know. Talk to Trish. Other questions? Yeah.
How much of our food waste from the various sources is currently either digested or composted. And I mean, we're looking at grocery stores that throw food away, packing houses, restaurant waste or food scrap. And regs coming by, I think, 2020, 2025. Regulations come online.
Yeah, so the question was, to repeat the question was, how much food waste do we currently reutilize, do something with, and if the regulations are coming in 2020 in a lot of these states, there's no federal regulations, it's all state passed, what are we ready? And the answer is no. So Massachusetts was supposed to come online in 2018, it didn't because there was no place to put it. And so, so it got pushed back. So we're not ready. And so Massachusetts, when they had this new regulation that said, okay, grocery stores, food production process by 2018, it can't go to landfill. And back because there was no place to put it. And so I think this is an industry that we're going to see grow, because I think if we look at the U.S. and the food waste that we have, it's estimated that 33% of our food supply is wasted. It's the highest by so much than anywhere else in the world. And so I think this is something that we're going to have to tackle. And so the first is, what food can we put to food banks? You know, what food can we reuse? Because some of this is wasted, you know, in the field or in production processes, or it could be reused from supermarkets. It doesn't look pretty, you know. So some of it can be reused, but it's the one difference is in the U.S. we all have, or we mainly, a lot of us have garbage disposals. I spent the last couple months in Europe. Every single place I stayed, in Germany, France, you know, we traveled around, none of them had garbage disposals. They don't have them. So their waste is actually source separated there. And then the waste, they actually get paid by each trash can they have, and their food waste is collected separately. And so there's an incentive to divert waste, and it's required by law. If you have food waste, you can get fined. We don't have anything like that here. And so it would take a real mindset, I think, for us to have that. So I think that's why the only one, there's a couple municipalities, Seattle and some other places, that have places and plants for residential diversion requirements. But most, the US, it's mainly focusing first on industry, because it figured that's something where there's less change of behavior necessarily needed, and there might be a financial incentive, because right now they're paying to go to landfill. And so it's already a cost to them. So if they can reduce the amount of waste that actually is wasted and donate some of that, and then instead of going to landfill, if they could get some sort of incentive to go somewhere else instead. Or it could be punitive. It depends on how the regulations are written. But the answer is we're not ready, and we should be. So I really think that's where the industry needs to focus, because I think those that can get ahead of the game, I think will do well, depending on the regulations.
I mean, that's a huge number. 33% of everything gets thrown away right now.
It's not all thrown. I mean, some is in the field, so it doesn't get harvested. Some is in, some is wasted. Some is put in the grocery store, but nobody ever eats it. It gets thrown away. Some is taken to my house and it rots in my fridge. Some is, for example, my kids eat 2 bites, and then I've got a whole sandwich. And the thing is, am I composting that? Am I putting that away? That's nutrients that we took a lot of time and effort to uptake into food. And are we really thinking, like, what can we do with this? And so, again, I lived for a while in Costa Rica. What did we do there? We threw it outside and the chickens ate it. Like, it always went back. Like you did. You just threw your food out. And again, we're not going to do that here. But what is it that we can do to try to get nutrients back into the fields and all the food, instead of it going to landfills or going to a wastewater treatment plant through the garbage disposal, and us using a lot of electricity to treat it? So it's an issue, something to contemplate.
Okay, any other questions? Thank you.
All right, thank you very much.